Here. Intro to functions of several variables. This is module 3 out of 5 big modules in this course. And we're starting this new chapter. It's really exciting. I love this stuff. So we're going to look at what it is to be a function of several variables. But before we do, let's do some review, because we're going to be introducing a new function today. But let's remind you of the functions that you already are familiar with. So here's the review. So far, you've studied 2 types of functions. One of them you've done in like algebra as well as calculus 1 and 2, and those are known as functions of a, running out of room here, single variable. You're very familiar with those. What do you mean? Well, like y equals f of x. That's a function of a single variable. The single variable there, that is x. So y is the function of a single variable, and the single variable is x. Fine. What's another function you're familiar with? Well, you're probably not as familiar because you just studied it in the last chapter. Vector valued functions. Yes, indeed. Vector valued functions. Different kind of function. So let's do the function machines for these really quickly. This is review. You've seen me do this before. So the function of a single variable, y equals f of x, you feed it something and then it expels something. Does anybody remember what you feed him? I'll give you 3 options. Do you feed him a point, a real number, or a vector? This is a function of a single variable.
A real number.
Good. X, a real number. So you feed him a real number x, and after he eats it, he poops out, he poops out what? Does he poop out a point, a real number, or a vector?
It's a real number. That's y.
Good. Why? I'm having trouble with my a real number. So you feed it a real number, and the ranges are real numbers. Fine. Now, what about vector valued functions? So the function machine for those has a little bit different flavor. The notation is definitely different. We have a vector valued function, say r of t, and that has this notation: angular brackets, x of t, comma, y of t, comma, z of t. We'll do a 3-dimensional vector valued function, but you can have 2-dimensional. And you feed the vector valued function t, usually stands for time, which is a real number. The output is a vector. You feed it a real number and you get a vector of some sort, say, some constant vector a, b, c. Okay, so we're going to introduce functions of more than one variable now. So we're going to see a different kind of function machine soon. But before we do, let's go through some notation for it. All right. I claim you already know functions of more than one variable. You've already done work with it, even though nobody told you that. Really? Yeah. So the good news is that it's kind of review. Well, what do you mean? Well, look, when we did work is equal to force times distance. That has work, a function of 2 variables, force and distance. There you go. How about when you're dealing with volume of a cylinder? V for volume, that's a function. And he's a function of 2 variables, r, the radius of the cylinder, and h, the height. So there's a function of 2 variables. Yay. What about the volume of a rectangular solid? V volume equals length times width times height. You've seen that. That's a function of 3 variables, length and width and height. So let's go over the notation for it. When you're,
because they're independent?
Yeah, all 3 of these are independent. True. So let's look at the notation for functions of more than one variable. If you're doing a function of 2 variables, you still can use f for function, and then you'll still have parentheses, but inside the parentheses, you'll put the 2 independent variables delimited by a comma in there. So x comma y. And they're naming the function z, which is pretty typical. Z is a function of x and y. And then here's just a cute little example, x squared plus xy. Oh, okay, fun. Now, what about a function of 3 variables? Sure. And the notation would be f of parentheses x comma y comma z. And you're just indicating an x, y, and z are those three independent variables. And they named the function w. They may or may not name it, but that's very common. Just like when you did calculus 1, for example, sometimes they would just go, oh, f of x, right? But sometimes they would call f of x y. And then sometimes they would actually write y is equal to f of x. So you're familiar with all three of those notations for a function of a single variable. So we have similar when we deal with functions of more than one variable. They may just call it f of x comma y, okay? Or they'll just call it by its cute name z, or they'll actually write it all out. Z is equal to f of x comma y. So all three of those options can be possibilities when we're studying this concept, and they're all legit. So both of these examples are using notation in what's known as explicit form. Explicit. And you're probably a little familiar with the word explicit because when you, let me just show you an example, like y is equal to, as an example, 2x plus 17. Okay, that's a function given in explicit form, as opposed to implicitly. So when you have a function of two variables and it's written explicitly, you have z is equal to f of xy. So you have z equal to stuff that has x's and y's in it. In your calculus 1, explicit form meant you're able to isolate y on one side of the equation and x and any numbers that you need on the right. But what is it to be? So this is explicit. What's implicit? So implicit is where you may not have the y isolated. So if I rewrote this little function and put the 2x, I subtract 2x from both sides, when we write it as, say, negative 2x plus y equals 17, that is known as implicit form. Okay? That's implicit. So you will be working with explicit and implicit forms in this class. So if you have the explicit function of two variables, you're able to isolate the z on one side of the equation and all the x's and y's on the other side. But if they do have everything, say, rewritten where you get, let's say you subtract the z from both sides of the equation like this, and rewrite it as fxy minus z equals 0, that's implicit. Or sometimes what we're going to do is all the junk on the left-hand side, all that stuff, now has x's and y's, and well, it has one z in it. So we'll rename that big F x comma y comma z, because that's a big old function of three variables equals 0. That's another way to represent functions. Okay, now let's talk about domain and range. Once you're introduced to a new function, it's the next step. It's logical. Talk about domain and range. What are the inputs and what are the outputs? So when you're feeding the function of two variables something, the domain, it turns out you feed it points in R2, which is 2 dimensions. Okay, so you feed it. So this is the domain in the XY plane here. You pick little points here in the XY plane, and then you feed it to your function, and he'll eat a point, and then his output is a real number. So a real number will correspond to a point. So what's happening here is your function f assigns to each point here in the XY plane a real number z. This isn't really complicated, although it is brand new. Okay, so let's do the function machine diagram for a function of two variables, shall we? So I just love these function machines because they kind of show you what's going on. So what do you feed this function z equals f x comma y, a function of two variables? You feed him a point. You feed him an ordered pair, which is typically in the XY plane. And once he eats that point, he outputs a value z, which is a real number. Now that value z, that real number that corresponds to the point, when we graph this function of two variables, that z value will be the altitude that corresponds to the point. Yeah. And there is the function machine. So let's evaluate a function of two variables at some points. So here's a nice function. It's not that great, but fx comma y equals 3x squared minus 2y. Great. What if you fed him the point 3, 2? So the notation looks like this. F evaluated at 3, 2. So F parentheses 3, 2. And you're just going to use substitution, just like you would when you evaluate a function of a single variable at a number. So everywhere I see an x in the equation, I will substitute the x value here, which is a 3, because that's what they gave me for the x. And then for the y, I substitute a 2. So 3 times 3 squared minus 2 times 2 gives me a z value of, oh dear, 27 minus 4, which is 23. And I'm done with part A. That was pretty easy. How about letter B? What if I evaluate this very same function at the point -1, 4? Okay, the notation is f, parentheses, -1, comma, oops, I can't write today. -1, 4. And again, direct substitution. 3 times -1 squared minus 2 times 4. And that's going to give us, what, 3 minus 8, which is -5. That would be an altitude corresponding to the point -1, 4. You get negative altitudes. You get a positive, negative, or 0. Okay, now what if I fed it a point with a fixed x coordinate 5, but some variable coordinate y? No problem. Same thing you're going to do. You're going to evaluate at 5, y. So you'll substitute a 5 in place of the x, any x's that appear in your function, and you'll leave the y alone. And so you'll get an expression in y, 75 minus 2y. There's your answer for letter C. That's legit. And similarly, letter D, suppose we have a variable x, but a fixed value for y. Okay, f evaluated at x, 2 is 3x squared minus 2 times 2, and that's some expression, 3x squared minus 4 in x. Now, letter E is a little bit more involved because you're doing more than just evaluating your function at a single point. You're going to evaluate what's known as the difference quotient. The difference quotient is very famous in mathematics, and it shows up in limits and things like that. Very famous. So you're going to evaluate f at x plus delta x, comma y, and then you'll subtract from that f just evaluated at plain old xy, and then you'll divide that entire numerator by delta x. Okay, so I'm going to do this somewhat slowly. So here's the deal. We're still dealing with this function up here they gave us, 3x squared minus 2y. So if we evaluate the function at x plus delta x, comma y, we're going to substitute x plus delta x in place of x, and we'll leave y, just y. So there's the function evaluated at x plus delta x, comma y. And then we're going to minus, we'll subtract fxy. Well, they gave us fxy. That's just 3x squared minus 2y. And the parentheses here matter because we are going to have to distribute the negative in about 2 seconds. And then this whole thing is all over the denominator delta x. Okay, it's getting a little messy here. So I'm going to distribute this minus. I'm also going to have to FOIL the x plus delta x squared. So I'm going to start doing that now by multiplying x plus delta x with itself, and I still have the minus 2y. And then after distributing the minus over fxy, I see that I can do a little bit of canceling here because negative 2y plus 2y adds to 0. Okay, now what? Now this is where the algebra can kill people. After you FOIL this product, don't bring the 3 in yet. Oh, no. We'll deal with the 3 later. You're going to get x times x is x squared x times delta x is just x times delta x. Delta x times times x, that's delta x times x, plus delta x times delta x. Well, that's delta x getting squared, that whole mess. Okay, and then you still have this minus 3x squared over there in the numerator, and this whole mess is still all over delta x. Are we done yet? Oh, heck no. We got more algebra. This is very common. The two middle terms here, when we did the FOIL, those are like terms. So one, one of those plus another one of those is two of those. One apple plus one apple is two apples. So that is going to end up simplifying to 2x delta x. And now I'll distribute my 3 over the brackets. So I'm going to have 3x squared plus 3 times 2, which is 6x delta x, plus 3 delta x getting squared. I know, this is just nuts, sorry. And then minus 3x squared. And that's still all over the denominator delta x. Are we getting close to being done? Yes. The 3x squareds cancel. And then the two terms that are left in the numerator, I'm going to factor out a common factor. And there's more than just delta x as a common factor, but for now, I'm just going to factor out the delta x only because I can. And then I'm dividing by delta x. So the beautiful thing that happens is the delta x's cancel. And my final answer to this big mess is 6x plus 3 delta x. Now, eventually we'll do derivatives, and this was the difference quotient for something known as a partial derivative with respect to x, and we would take the limit as delta x goes to 0, and then we'd end up with 6x. But there's no limits here in this problem, so don't do a limit when they didn't say. Okay. All right, let's do some more domain stuff now. So remember the domain rules that I gave you back for vector valued functions? Those are all still in effect. And what I do expect is for people to write out what is so for your domains. Now, I claim the domains for functions of more than one variable are a little easier than vector valued functions because you don't have to intersect the sets before writing out your final answer. You just put all the restrictions and delimit them by commas using set notation. What the heck did I just say? I don't even know. No. So let's go through how to do that by doing an example. Okay, you don't do interval notation. There's no intervals when you do functions of more than one variable. So no interval notation at all. It won't even work. You use set notation. So take a look at this baby here. This is a function of two variables, and it's pretty hellacious. And we have two things we have to worry about. One thing we have to worry about is we have an even radical. So what's one thing that we need to have to be true? Well, you never want to take square roots of negative numbers. So I actually want you to write out the inequality. And some of you just drew pictures for me on the exam, and those are nice, but pictures are not proof. So you may have had some points taken off. You didn't physically write out the inequality that I like to see. Now, you can rearrange this inequality if you want to. Sometimes you'll see a lot of textbooks will add 9 to both sides just to make it visually more appealing. And we'll see in a moment when we actually have to sketch the domain. Now, we have another worry because you never want denominators to equal 0. That's horrible. So this little x, we don't want him to be equal to 0. That would be bad. So the final answer for letter A, and be careful because all the notation matters, and I want to see this on any handwritten work. You're going to use curly braces because that's set notation, so curly braces. And then you're going to put all the ordered pairs, so you're going to put parentheses x comma y, not f of x, y. We're not dealing with the function. We're dealing with the set of ordered pairs that make up the domain. And remember, the domain for a function of two variables are points with an x and y coordinate. So and then you'll put a bar. Some textbooks, instead of a bar, they'll put a colon. I don't care, one or the other. You can put a colon there or a bar. It's similar notation. And then after the bar, tell me all the restrictions delimited by commas. Well, I've got the x squared plus the y squared greater than or equal to 9, comma, x not equal to 0. And I'm done. This is the final answer for part A. That is his domain. All the x, y coordinates that fulfill on this criteria. Letter B. Okay, letter B, we got a lot of problems, a lot of things to worry about. So this function of two variables, we have a denominator that we don't want going to 0. We have a logarithm, and you know logarithms require positive arguments. And then we have another one of those even radicals. Now, good news for us, there's no restrictions on this particular sine function. Sine of xy, you can feed them anything you want. I don't care. So what are the three issues that we have to worry about? Well, 4y squared minus 2, we do not want that equaling 0. If I solve this for y, watch out, be very careful. I get y squared is equal to a half. But then actually square root both sides. And when you square root both sides, what do you always have to remember? Anybody remember?
Plus minus.
Mm-hmm. Yeah, exactly right. So you need the plus or minus. So y, and this is a not equal, not equal, not equal. Y not equal to plus or minus the square root of 1/2. So that's one of the restrictions. And then we have the logarithm 2 minus x minus y has to be strictly greater than 0. And sometimes you might see textbooks add the x and y to the other side of both sides of the inequality. And then sometimes they'll even rewrite it again, x plus y less than 2. Either way, they're both fine. And then finally, the radicand of the even radical, you need the radicand x to the 4th minus y to the 4th greater than or equal to 0. So now how do you write your final answer to letter B, especially if you run out of room like I always do? So you're going to use the curly braces. So here's the answer to letter B, curly braces, and leave a lot of room here because we have a lot of restrictions. Big old curly braces. The set of all ordered pairs, x, y, in parentheses, x comma y, such that, that's the bar, y not equal to plus or minus 1 over square root of 2, comma, x plus y strictly less than 2, comma, x to the 4th minus y to the 4th greater than or equal to 0. Big old set notation right there. That is a big old answer. Yikes. But it's everything we need. Now, letter C is a little bit trickier because we have a function of 3 variables. Oh, yeah. G of x, comma, y, comma, z. All right. Well, what of it? Well, you look for any restrictions that are needed. And I see 2 things at the same time. I see an even radical. That's something to worry about. And I also see that the denominator could go to 0. Now, this was a problem that was on some of your midterm, and I say some because there were 2 versions, slightly different, but challenge level the same. So you normally, if you were just dealing with any old even radical that was in the numerator, you'd go, hey, I need 9 minus x squared minus y squared minus z squared greater than or equal to 0. True. But because this guy is in the denominator and you never want denominators going to 0, instead of the greater than or equal to, this one's going to be strictly greater than. So that's the big difference. And then I'm going to add x squared, y squared, and z squared to both sides of the inequality to make it look a little prettier, like so. And then I'm going to even rewrite it again because the typical thing is to put the x squared plus y squared plus z squared, less than 9. Okay, now how would you write letter C's final answer? You're going to use curly braces, big old curly braces, but now you're going to do an ordered triple. Well, how come an ordered triple? Because this was a function of 3 variables, and so his domain is the set of points that live in R3, or 3 dimensions. So the set of all ordered triples such that, and we only had one restriction, we needed x squared plus y squared plus z squared to be strictly less than 9. And there's your answer to letter C. That's it. That's your domain. Now, what about sketching domains? Like when we were sketching domains for functions of single variables, you would, shade in the number line, various portions of the number line in intervals. But here we're not dealing with intervals. So if you're going to graph the set that's given by this domain, how would you do it? So I want you to see that, and this will give you a better feel for when we start graphing these functions of more than one variable, which is coming up in less than 5 minutes. So take a look at the part A answer. What about the part A answer? Where was it? It's here in red. So that answer requires any points living in the XY plane such that x squared plus y squared is always greater than or equal to 9, and we never want x to be equal to 0. So how would you graph that? That's nuts. And they graphed it right here for you. What do you mean? You'll notice that there's a dotted line on the y-axis. Well, how come? Because if you graphed x equals 0, that would be the line that lives on top of the y-axis. But remember, we don't want x equaling 0. So any of the points that are on the y-axis are forbidden. This function is not allowed to eat them. He's on a diet. That's one thing. Then the other thing is, what about this x squared plus y squared greater than or equal to 9? Well, first graph x squared plus y squared equals 9, which you're all familiar with. It's a circle centered at the origin of radius 3, and that's why they got this thing going. And there's a solid line on the boundary because equals 9 is okay. And then the greater than or equal means you're going to shade in all of the values outside of the circle except nothing that lives on the y-axis, because remember, the y-axis is forbidden, not allowed. So the picture of the domain is kind of cool. It's the blue shading that you see there. Any point that lives out here, you can feed it to your function. Like for example, how about the point, I don't know, 4, 5, way out here? Is that okay to feed the function from letter A? Yep, he can eat that one. He's okay to go. All right. Now a little bit higher level thinking for you. What about that part C thing? Okay. When you graph functions of more than one variable, you have to be careful. Functions of 2 variables, which we deal with mostly in this course, you need 3 dimensions to graph. You'll see in a moment because they're going to graph as surfaces. Functions of 3 variables, you would need 4 dimensions to graph. And I'm sorry, we can't visualize that. We cannot visualize graphing a function of 3 variables because we would need 4 dimensions, okay? So, it says if we were trying to graph the function for part C, how many dimensions would we be required? 4 dimensions. You can't visualize the graph, okay? Now, the domain you can graph, because the domain of that G function lives in 3D, because he's the set of ordered triples that satisfy this answer we got down here. So you can graph G because you can't graph G itself, okay? Because of this. Oh, hang on. I should have put the 4 dimensions here. Sorry, I was answering. So you can't graph G because he needs 4 dimensions. And for the domain, you only need 3 dimensions. Okay, so the domain you can graph, but the actual function you can't. So what would the domain look like? Well, it's this set, curly braces, all ordered triples, that x squared plus y squared plus z squared less than 9. Does anybody remember from like the first week of class, if that inequality were an equal sign instead, what the graph would look like? Anybody recall what that would be?
I think it's an ellipsoid, right?
You're close. It's a perfect ellipsoid. It would be a sphere. A sphere of radius 3, centered at the origin. If that were an equals. But it's not an equals, darn it. It's strictly less than. Ah, ha, 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 ha. So what that means if we were to graph the set of all points, x squared plus y squared plus z squared less than 9, the boundary of the sphere we'll put as a dotted boundary, because that means you're not allowed to include the boundary of the sphere. But we'd shade in all of the points that live inside the sphere. So it'd be like this ball of points. Any point that lives inside that sphere, okay to feed your function. We like it those, but we can't eat the boundary of the sphere or anything outside the sphere. Okay?
Is T the fourth dimension?
No. X would be the first dimension. We're
I'm
not
sorry.
considering T anymore. That was for vector valued functions.
I'm sorry. I'm just talking in
Okay.
general.
Yeah,
Like,
no, I understand. Some people like to claim that T is the fourth dimension, that we're all living in 3D and overlaid on top of our three-dimensional world here, we have time. So time is the extra dimension. But okay, yeah, that's fine, but you still can't visualize the 4 dimensions. Like you can't graph it. Although I've read some really weird books where they talk about string theory and the physicists try to graph like 6 dimensions or 11 dimensions. And if you're into computer science, you can maybe get behind this because you do have multi-dimensional arrays. Yeah, like Java lets you do 6-dimensional arrays. Heck, why not? Okay, let's graph. You guys ready to graph or no? Yes, no? So how do you graph a function of 2 variables? Well, it's not easy, and I'm luckily not going to ask you to do a lot of graphing in 3D, okay? As I mentioned before, you should know how to graph a plane, though. And, you know, a sphere centered at the origin, you should probably know how to graph that surface as well. So planes or surfaces, you should pretty much know how to graph, and spheres. Now, speaking of planes, like here's an equation of a plane: 2x plus 3y plus 6z equals 12. That is a function of 2 variables, but it's given in implicit form. Why implicit form? Because they didn't solve it for z. So this is, you're already familiar with a very nice surface in space because you're familiar with planes. And so the equation for a plane is written in implicit, we call this implicit form because we didn't isolate the z on one side and all the rest of the junk on the other. But you could, you get that you could very easily write it in explicit form if you simply subtracted 2x and 3y from both sides and then divided both sides of the equation by 6. Your plane equation, it's still a plane equation, it's just written now in explicit form. That's all. Still a plane, nobody changed it. Okay, but now it has that flavor of z is equal to f of x comma y, because you got the x's and y's on one side of the equation and the z on the other. Okay, so now let's talk about more graphing. So what you do when you graph a function of 2 variables is you graph an ordered triple. So you first feed the function a point in the xy plane down here. Here's the domain. And then it gives you an altitude. It gives you a z value, you know, how high off of the plane, or you may go in the negative direction. And then you plot this ordered triple in space, x comma y, and the z coordinate is f, evaluated at x, y. And so once you get all the collection of points up here, you kind of connect them all together and you get a very lovely surface right here. So there's a lovely surface. Notice the surface is hovering over the domain, and that better always be the case. If somehow your surface is hovering over some points that don't belong in the domain, that's impossible. So you can kind of think of this, these are your ancestors in heaven, and they're hovering over you, or you're down here on planet Earth walking around in the XY plane. I just think of it that way. You don't have to, I don't know. Sorry, but you don't go that route. So what about projections now? You guys know about projecting vectors onto another vector, right? We talked about that. And I like to think of a projection of a vector onto another vector as the shadow. And we talked about this. Let's say here's V, and let's say here's U. When you project U onto V, you can kind of think of a bright sun shining up here. And the shadow that you will make on the V vector, like down here, this red vector I'm drawing. That's the projection of u onto v. But folks, you can also project surfaces. Oh, yeah. So if you project this surface onto the XY plane here, you'll get this shadow down here, and that gives you the domain. Okay, so that's what they're talking about when they say the surface is projected onto the XY plane is going to give you D, the domain. Now, just like functions of one variable when you took pre-calc and all that, functions of two variables have to pass the vertical line test if you're going to call them a function. Otherwise, you know, they're not functions. So you'll probably remember that from pre-calc. So check out this ellipsoid. This ellipsoid does not pass the vertical line test because the vertical line intersects more than once. However, this lovely elliptic paraboloid, this is a function. And when we say is a function, not function of x, function of x and y, because this is functions of two variables we're talking about now. Now, even though this ellipsoid is not a function of x and y, it's still a very lovely graph, and we're still going to do business with it. Okay. So now that you're kind of apprised of some of this, I want to show you some really cool functions that you can graph. And you can graph functions, we talked about this by going to GeoGebra and graphing, but I want to show you this new calc that I have. Let me just show you some fun graphs here. So if you check out what I have here on the screen, you'll notice that fxy is equal to ax squared plus by squared. So if we let a and b be different numbers, the shape of the graph will change a little bit. But the basic look of the graph, you can see it here, it kind of looks like a saddle, a horse's saddle. I think it's what we call a hyperboloid. But if I slide the slider, can I do that? It'll let me. No, maybe not. This one's not letting me. Use the sliders. No, I'm not getting any sliders here. Let's go down. No, not letting me. Okay. It's stopped. So I can't do that one. Let's try another one. Here's one that looks like an eggshell, and that one won't let me do the sliders either. Yeah. And then here's another one that's a logarithm, which is kind of cool. But you can graph all kinds of things. So what I'll do here is I'll just show you some fun stuff. Let me go to my new calc. It's a little bit more fun. So this software that I have, you can do stuff in 3D, but you can, yeah, hyperbolic parabola, yeah, the Pringle shape, exactly. So one of the things I like to do, you know, in my software here, I could just go, you know, hey, y is equal to 2x plus 10, you know, not very interesting. It's a line, fine. Okay. But I can also graph things in 2D, or 3D rather. So what can I also do? Well, I can go like, you know, z equals, you know, just something fun, 3x squared plus 2y. I have no idea what I'm graphing right now. Whoa, there it is. Okay. And I'm giving the surface in what we call explicit form. And this particular software, wow, that's kind of cool. This particular software allows me to change colors if I have explicit form. I can, you know, go candy stripes. Woo, candy bars. Oh, nice. Okay, so that's fun. What's really kind of cool about this software, however, is I can graph it. Well, I can graph planes. Let's see if I can do a plane. 2x plus 3y plus z equals 6. I don't know. Okay, so there's a portion of a plane, and that's a nice surface. Woo. Okay, not that interesting. Oh, nicer color. Okay. So what else can I do here? So this is where it gets kind of fun. I can do implicit form. So what if I go sine of xy? How about less than? I can do a less than here. This is kind of fun. Sine x plus sine y. Oh, what do we got here? Whoa, that is cool. Check that out. Yeah. So that's an implicit function. You know, you have X's and Y's in there only. Isn't that neat? You gotta admit, I can zoom out. Let me see it. Pretty cool. All right, what about 3D now? So what if, now I'm going to put a z into the situation. So what about sine of xyz equals, I don't know, x plus 2y plus 3z. This is going to give me a surface. It's given, I'm giving it to it implicitly. Okay, there it is. Oh, that's kind of nice, kind of pretty. It's a nice surface. See if I can, it's because it's implicit, they don't give me all the color combo changes, so that's kind of a bummer. All right. And, you know, we're going to learn about different surfaces and different coordinate systems. So I don't want to freak anybody out too much right now. You know, we're going to be doing polar coordinates and stuff like that. And so it's going to be really fun. So this software is called Pacific Tech, and you can go look it up on the internet. I don't know what they charge for it now. But back in the old days, it was $60, but that was a long time ago. Okay, fine. Okay, so enough with this. Let's get rid of it. It does look pretty weird. All right, fun times. Okay, so what about surfaces? Well, we're going to have fun and play with surfaces like for the rest of the semester. So it's kind of fun to get a look on it, on what we're looking at. So it's just cool, fun times. Okay, let's do something that I typically don't ever ask you to do on exams and stuff like that, which is good news. And that is finding ranges. I'm more interested in having you find domains, not ranges. But, you know, range is a very important thing. You learned it in pre-calc and so on, and they asked you, you know, to find the range of a function of a single variable. So what about finding ranges of a function of more than one variable? Sure, we could do that. So take a look at this function. Z equals f of x, y, square root of 16 minus 4x squared minus y squared. And they graphed it on the next page. So you can actually see the surface. And it looks like the upper half of an ellipsoid. Somebody sliced it in half. Great. So they said describe the graph. So there it is. It's in the upper half of an ellipsoid. Fine. So what about the domain? Let's do the domain and we'll do range. Well, domain is, and we have an even radical. So if we're going to do, it's implied that we need the 16 minus 4x squared minus y squared to be greater than or equal to 0, because we don't want to take square roots of negative numbers, at least not in this class. So the D, the domain, is the set of all points lying on or inside the ellipse that's given by 4x squared plus y squared equals 16. And if you had to graph this ellipse and you get it in the standard form, you divide both sides by 16, and you'd have this ellipse centered at the origin in standard form. So what about Z though? Well, Z, if you look at what Z is here, this radical can't get any bigger than the 16 because it's 16 minus some things that are getting squared. So the biggest this can get is square root of 16 minus 0, which is 4. The lowest it could get would be 0 because you don't want to take square roots of negative numbers. So Z essentially is bounded above and below by 0 and square root of 16, which is basically the same as 0 and 4. So the altitude can't get any higher than 4. And the lowest altitude is 0. You can see that because when you're graphing the surface on the next page, the lowest altitudes are the points that are sitting here on the XY plane themselves. Those guys have a Z coordinate of 0, and any other point on the boundary of this ellipsoid has some non-zero positive altitude there, right? And so we're done. We've got the range. The range is Z goes between 0 and 4, inclusive, and we're done. Woo!